Hello everyone, sorry that this video is coming out a bit later than expected or hoped. I hope that's not too annoying and I apologize for it, but let's get into it. We're starting with our first video on our new unit, trigonometry. Trigonometry coming from, I'm pretty sure, the ancient Greek's word meaning trig meaning triangle and metry meaning measurement, so we're literally talking about triangle measurements. I think that's true. Read it somewhere once. Anyway, let's start with looking at the stuff we've been doing in class over the last couple of days on similar triangles. So let's say I've got two triangles, and we're going to assume that these two triangles are similar. And they're both right-angled triangles, and I'm just going to label the corners here. Okay, now what do we know about these two triangles if we know that they are similar? We know two things. The first thing we know is that all the corresponding angles are the same. So if we call this angle theta, then we know that this angle here will also be theta, because that's one of the properties of similar triangles. All the corresponding angles are the same. The other thing we know is that the corresponding side lengths all have the same ratio, the ratio of some scale factor k. So the way that I can write that is, let's say this side length here, AB, the ratio of this side length AB to this side length DE, so AB over DE, that's going to be the same as the ratio between any two other corresponding side lengths. So that's going to equal, for example, the ratio of AC, this side length here, to DF. Now, if we follow through with this thought the whole way, then it's going to give us a really important result. We can manipulate this equation a little bit if you want to think about it algebraically, or if you'd prefer to think about it more graphically, then I'm sure if you stare at these two triangles for long enough, you'll arrive at this same conclusion too. And that is that if these two triangles are similar, not only are the ratios between corresponding side lengths on the different triangles the same, but the ratio between two side lengths on the same triangle will also always be the same. In other words, I can manipulate this formula to say not only is the ratio of AB to DE going to be the same as AC to DF, but the ratio of AB to AC is going to equal the ratio of DE to DF. Let's think about what that means. It means the ratio of this side length to this side length is going to equal the ratio of this side length to this side length. And if that's true for similar triangles with this same angle theta, then it must be true of any right-angled triangle with this angle theta. So we get this really important result, which is that if I know the angles in my triangle, so I've got a right angle and I know the other angles as well. I only need one other because I can work out the last one if I want to, using the fact that all the angles equal 180 degrees. So but let's stick with the right angled triangles for now. If I have a right angled triangle and I know one of the other angles, then I don't know what the other side lengths are, but I know what the ratio of one side length to the other will be. Because if the ratio of this side length to that side length is the same for every similar triangle, then it's the same for every triangle with every right angled triangle with this same angle theta. And the thing that we use in this specific case to represent that is this idea of the sine of an angle. Sine of an angle theta, which we abbreviate sine to just S-I-N. I know, huge abbreviation, really saving us a lot of time there, dropping that E. So sine theta, that represents, this is, if you put sine theta into your calculator, it will give you a number. That number represents the ratio of this side length to that side length. So in this case, sine theta equals the side length AB over AC or the ratio between DE and DF, because those two things are the same, we've established that already, for every single triangle, every single right angled triangle with the angle theta. This will hold true. And we don't only know that for the ratio between these two side lengths, we can also know it for the ratio between any two side lengths on the triangle. And of course you know where I'm going with that. I can also write, I have this other one, the cosine, which we abbreviate to cos. I know that cos theta, that also just gives me a number, and that number is equal to the ratio between these two side lengths, the side length BC and AC. The ratio between these two side lengths equals the cosine of the angle. And tan theta, short for tangent, the tangent of the angle, that equals the ratio between AB and BC. Let's summarize this all on a new sheet of paper so that it's all a bit cleaner. And I'm going to give you a way of conceptualizing what sine, cos, and tan actually are so that we can take that going forward and make sure that we never get confused and use it the wrong way. So I've got a right angled triangle. Didn't draw that very well, but assume that it's right angled. And I've got an angle here, theta. Now, if that is my angle theta, then I'm going to label all of the side lengths of this triangle in relation to that angle. So this side length here, the one opposite the right angle, that's always the hypotenuse. The side length over here is the one that's not the hypotenuse, that is next to or adjacent to my angle theta. So this is the adjacent side length. And this is the side length that's opposite to my angle theta. So we call it the opposite. Mathematicians are very original in their names. So I've got my angle theta, I've got the hypotenuse, the opposite side, and the adjacent side. And now I want you to think that we have three machines. And you can think about this as three like computer programs, or three machines, let's call it. One of them is the function sine, one of them is the function cosine, and the last cosine, and the last one is the function tangent. And each of them has an input and an output. An input and an output. And for each of them, I stick something into the machine and something else pops out. And what I stick into the machine for each one is the angle, theta. And for each one, what pops out of the machine after it's gone through the function that the machine, all the stuff that the machine does to it, the function, what pops out of it is different for each one. So what pops out of the machine for the sine function is the opposite side over the hypotenuse. So the ratio between the opposite side and the hypotenuse is the number that pops out of the machine. For the cosine, the number that pops out of the machine is the ratio between the adjacent side and the hypotenuse. And for the tangent function, the number that pops out when we apply the tangent function to the angle is the ratio of the opposite side to the adjacent side. And you all know where I'm going with this as well. We can summarize this in an easy to remember way using the mnemonic SOHCAHTOA. SO telling me that the sine of the angle is the ratio of the opposite to the hypotenuse. Ka telling me that the cosine of the angle is equal to the adjacent over the hypotenuse. And toa telling me that the tangent of the angle is equal to the opposite over the adjacent. Now, the last thing that I want to go through is that we can also, of course, go the other way. We can go backwards through our machines. We can apply the opposite function to our we can apply our function in the opposite way. In other words, we can kind of flip this upside down, and instead of putting in an angle and getting out a ratio, we could put in a ratio and get out an angle. But in order to do that, we need to we're flipping something upside down, which means we're doing the inverse of it. So if we're going the opposite way, then we are applying the inverse of each one of these. So inverse tan, inverse cos, or inverse sine. And I'll just show you really quickly on your calculator what that looks like. So we've got here sine, cos, and tan. And above each of those, I don't know if you can see in the video, in little yellow writing, we've got sine raised to the power of -1, or inverse sine, inverse cosine, and inverse tan. So we can either, let's say we're looking for the sine of 60 degrees, gives us 0.866. So that means that if the theta is 60 degrees, then the ratio between the opposite and the hypotenuse is 0.866. And then if we say the sine to the -1, or inverse sine of 0.866, so I'm putting it in the opposite way, and I'm saying if that's my ratio, then it's going to give me the angle of roughly 60 degrees. Okay, like I said, introductory video, pretty basic. I'm sure everyone is pretty on top of this stuff already, but good to go back to basics. And this is all we're going to need in order to do exercise 10A, which we're going to get stuck into in class tomorrow.